Now, if you think about that for a moment, you should say that's not possible. The amount of melt per weight of chemical has to be a constant. If you double the amount of deicer, you have to double the amount of ice melting. So the fact that you're seeing the ice melting capacity increase in the test is another indication of the error inherent in the test method. But notice that as I go to higher application rates, it starts to converge. So by going to higher application rates, I am able to converge on the true value of the total ice melting capacity and reduce my measurement error. And this slide here shows you the effect of these test modifications on the measurement error. What I'm plotting here is the coefficient of variation. So this is basically the percent uncertainty in my measurement. And this is plotted at 3 different measurement times and at 3 different application rates. So notice that as we go from 1 hour to 5 hours to 7 hours, my test error drops. Similarly, within any one of these measurements, as I go from 4 to 8 to 12 grams, again, my measurement error drops. So by simply increasing the application rate and measurement time, I'm able to get much more precise and accurate measurements. Now, this question may occur to you. Are these modified test conditions realistic? And the answer is no, they're not realistic at all. If I go to an 8 to 12 gram application rate in the SHARP test, that's equivalent to about 2,500 to 3,800 pounds per lane mile of salt. Obviously, that's enormously higher than what we actually use in practice. And you might be tempted to say that this invalidates the test, that this data is no good if I'm that far outside of what we really do in the field. But be a little bit careful before making that conclusion. Remember what we're trying to measure. We're not trying to simulate a de-icing event in the field. What we're trying to do, and all we're trying to do, is we're trying to accurately measure the actual ice melting power, the total ice melting capacity and the de-icing rate of a chemical. And as long as there's good contact between the ice and the chemical, as long as I'm measuring the melt per weight of chemical, I can put as much down as I want. It doesn't make any difference. So there's nothing wrong with this test approach. It's going to enable me to get more precise and accurate measurements. Now, in the process of doing that work, and so I wanted to introduce that initial ice melting capacity test work to you because in the process of doing that, we've learned some interesting things about the relationship between ice melting capacity and ice melting rate that I think are going to shed some very useful light on understanding the low temperature performance of de-icers and helping us to better understand or move towards optimizing performance at very cold temperatures. I'm going to circle back and end my talk by discussing that. But before I do, there's one other aspect of de-icer performance that I want to touch on, and that's de-icer longevity. De-icer longevity is something that we talk about a lot. We've got qualitative observations that we think some de-icers last longer under field conditions than others. But we don't at the moment have a standard industry test method to measure how long a de-icer remains effective once it's put down on the road. However, interestingly, there is a standard test method for measuring how long aircraft de-icers remain effective. The longevity of aircraft de-icers is measured by a method called the water spray endurance test, which I abbreviate as WSET. This WSET test is used to calculate what are called holdover times. The holdover time is the length of time a plane can sit after it's been de-iced before it needs to be de-iced again. So the plane goes through the de-icing station, gets hosed down with the de-icing fluid, then it rolls out onto the tarmac and waits for its turn to take off. Let's say it's snowing or there's freezing precipitation going on and the plane is stuck there waiting. Excuse me, the pilot needs to know how long can that plane stand there and be exposed to continuing freezing precipitation before the de-icer has been diluted and washed off and it needs to be de-iced again. Essentially, it's a measure of de-icer longevity. Now, they measure that the following way. They take aluminum test plates that are tilted at an angle, and this is to simulate the wings of an airplane. They apply the de-icing fluid to the wings, and they expose them to a very finely controlled rate of freezing precipitation in the form of a uniformly dispersed mist of supercooled water droplets. These droplets will freeze the moment they hit those cold aluminum plates. And they simply look and see how long does it take before the deicer fails. As precipitation begins, initially, of course, the deicer melts the precipitation. As that goes on, more and more precipitation dilutes the melt. It starts washing off the plates, and at some point it starts to freeze. And they define the failure as the time that it takes for the ice front to advance 25 millimeters down the front of the plate. Different aircraft deicers have different lifetimes. Type 1 fluids will have a WSET failure time of about 3 minutes, whereas Type 4 fluids will have failure times as long as 80 minutes. So we thought it was interesting that the aircraft industry measured the essentially effective lifetime of deicing fluids by this approach. And we posed the question, can we modify this test to make it better simulate the somewhat different conditions under which highway deicers are used? And can we learn something about how deicing fluids behave when they're exposed to continual precipitation, and how long do they last? Can we measure differences between them?